Welcome everyone! Today, we're diving deep into some fascinating and thought-provoking discoveries about Earth's gravity. These discoveries might sound like something out of a science fiction novel, but they're rooted in scientific research and satellite data. Recently, an unusual gravitational anomaly was found, and it could very well be the first of its kind. These anomalies are not only intriguing, but they also reveal hidden secrets beneath the Earth's surface that traditional geological studies simply can't uncover. The force of gravity shapes everything around us, and yet, there's still so much we don't understand about how it works across the planet. Now, you might be wondering, what exactly is a gravitational anomaly? In simple terms, it's a deviation in gravity from what we expect to find based on a theoretical model of the Earth. Our planet's gravity is supposed to be pretty uniform, but as it turns out, it's not. Gravity changes from one place to another, often in very subtle ways. These changes are so small that, in everyday life, we wouldn't notice them. But by using advanced technology, scientists can measure these tiny variations with incredible precision. In today's discussion, we'll explore this latest discovery, comparing it to similar findings from the Moon. And we'll take a deeper look at the fundamental force of gravity itself. But before diving into these exciting anomalies, it's essential to first understand how such discoveries are even possible. How do we measure gravity with such precision, and how do we detect these unusual changes? Most of the groundbreaking research into gravity anomalies comes from satellite missions, which have been carefully designed to measure gravity from space. One of the most influential and successful missions in this field is NASA's Gravity Recovery and Climate Experiment, or GRACE. This mission has been ongoing for more than 2 decades, and its main goal is simple, but vital: to map the Earth's gravity in detail and to find irregularities or anomalies in it. The GRACE mission has helped us measure gravity at a level of precision that was unimaginable just a few decades ago, and it's been one of the key tools in our quest to understand how gravity operates across the planet. Now that we have a basic understanding of what gravitational anomalies are, let's explore how scientists measure them. As I mentioned earlier, one of the most important tools in studying gravity anomalies is NASA's GRACE mission. The GRACE mission uses 2 satellites that are in orbit around the Earth. These satellites work together, flying just a few hundred kilometers apart, and they measure the Earth's gravitational field with remarkable precision. The way these satellites operate is quite fascinating. They orbit in such a way that they can detect even the tiniest changes in the distance between them. When one satellite flies over an area with stronger gravity, it speeds up slightly because the gravitational pull is stronger. As a result, the distance between the 2 satellites changes, and this change can be detected by the satellite's precise measuring instruments. This method allows scientists to create incredibly detailed maps of the Earth's gravity. However, it's important to note that gravity anomalies are often very small, sometimes only a few milligals. A milligal is 1/1000th of a gal, the unit used to measure gravity. To put this in perspective, the average gravity of the Earth is around 980,000 milligals. So, even a slight variation, such as a 50 milligal difference, represents a tiny change in gravity. These tiny variations, however, are highly significant in the field of geophysics. By detecting and analyzing these changes, scientists can uncover information about the Earth's interior structure. For instance, areas with stronger gravity could indicate dense materials beneath the surface, such as metallic ores or oceanic crust. Meanwhile, areas with weaker gravity might indicate lighter materials, like thick sedimentary rock or even massive basins filled with low-density sediments. What's truly amazing is that these variations can help scientists understand not just the surface of the Earth, but also the structures deep inside the planet. By mapping these variations in gravity, researchers can gain insights into things like the thickness of the Earth's crust, the position of tectonic plates, and the distribution of minerals and other resources beneath the surface. The GRACE satellites have been instrumental in helping us map the entire planet's gravity, providing a level of detail that was previously unattainable. And as you'll see, these measurements don't just help us understand the Earth, they're also a crucial tool for studying the Moon and other planets in the solar system. Now that we've discussed how the GRACE mission works and how it measures gravity anomalies, let's dive into the real-world applications of these findings. Gravity anomalies might seem like abstract scientific data at first, but they actually have a wide range of practical uses across different industries. Let's explore a few of them. One of the most significant applications of gravity anomalies is in the mining industry. As we mentioned earlier, positive gravity anomalies occur in areas where gravity is slightly stronger than expected. These regions are often associated with denser materials in the Earth's crust, such as metal ores or thick oceanic crust. By identifying these anomalies, mining companies can target areas that are more likely to contain valuable resources, like iron, gold, or copper. In addition to mining, gravity anomalies are invaluable to geologists studying the Earth's interior. For example, negative gravity anomalies areas, where gravity is slightly weaker, can indicate the presence of large basins, filled with light sedimentary rocks or thick continental crust. These negative anomalies often correspond to structures like oil and gas reserves. Since sedimentary basins are typically much less dense than the surrounding rock, they create gravity measurements that are lower than expected. By mapping these anomalies, geologists can pinpoint potential sites for drilling, leading to more efficient exploration for oil and gas. But gravity anomalies aren't just useful for resource extraction. They also play a critical role in understanding plate tectonics and the structure of the Earth's crust. The Earth's crust is constantly shifting due to the movement of tectonic plates, and gravity maps can help scientists track these movements. By studying gravity anomalies, geologists can identify faults, folds, and other geological features that are difficult to detect through traditional surface observations. Moreover, gravity anomalies help scientists study the Earth's mantle, the layer beneath the crust. By measuring variations in gravity, scientists can gain a better understanding of the mantle's composition and how it behaves over time. For example, gravity measurements can provide clues about the presence of hotspot areas where molten material rises from deep within the mantle to the surface, potentially forming volcanoes or mountain ranges. This is essential for understanding the processes that shape the planet's surface and influence its geology. The applications of gravity anomalies extend beyond geology and mining, though they also play an important role in climate research. As the GRACE satellites continue to collect data, scientists have discovered that gravity anomalies can provide insights into changes in the Earth's climate. For example, variations in gravity can be caused by the redistribution of water across the planet's surface. This includes changes in groundwater, the melting of glaciers, and fluctuations in sea level. In fact, GRACE's ability to detect even tiny changes in gravity has made it an indispensable tool for studying climate change. Over the years, scientists have used GRACE data to track shifts in water storage, such as the draining of aquifers or the melting of polar ice. These changes, while seemingly small, have profound implications for water availability, agriculture, and the overall health of ecosystems. By understanding how gravity changes in response to these shifts, researchers can predict the effects of climate change with greater accuracy. Now, let's dive into a specific and rather strange discovery that emerged from the GRACE mission data. For decades, scientists have believed that most gravity anomalies are linked to surface-level processes, like shifts in water distribution, changes in ice cover, or atmospheric variations. These processes are predictable and relatively easy to track. However, something unexpected and mysterious was recently uncovered: a gravitational anomaly that didn't fit the usual patterns. This anomaly was discovered after a detailed analysis of data collected by the GRACE satellites between 2006 and 2008. The peak of this gravity anomaly occurred in January 2007 over the eastern Atlantic Ocean. What makes this discovery so intriguing is the scale and nature of the anomaly. It stretched over an astonishing 7,000 kilometers, approximately 5,000 miles, suggesting that the source of this gravitational shift was something far deeper within the Earth than scientists initially thought. At first, scientists were puzzled. The anomaly was far too large and intense to be explained by surface-level changes like shifting water or atmospheric mass. When researchers ran simulations and compared the data to known processes, nothing seemed to make sense. The anomaly couldn't be attributed to any known surface causes. This led the scientists to consider the possibility of an underground source, deep within the Earth's interior. While the surface of the planet could certainly account for some gravity changes, the sheer scale and power of this anomaly forced researchers to explore the depths of the Earth for an answer. In fact, this discovery led scientists to rethink their assumptions about the nature of gravity. anomalies, and the forces at work beneath our feet. This strange event, which was missed for over a decade, is an example of how much we still have to learn about the Earth's internal processes. Even with sophisticated satellite technology and advanced models, there are still surprises waiting to be uncovered in the vast, mysterious depths of the planet. After months of analysis and puzzling over the anomaly, scientists turned their attention deep into the Earth's interior to find the source. They suspected that this gravitational shift might be caused by a process far beneath the surface, well beyond the reach of surface-level phenomena. This hypothesis led them to focus on a region known as the D layer, which lies between the Earth's mantle and its outer core. The D layer is a highly mysterious part of the Earth's structure, situated around 3,000 kilometers below the surface, and it's where the planet's mantle transitions into the liquid outer core. While this region has always been a subject of intense study, it has remained largely unexplored. However, after ruling out surface causes, scientists believe the anomaly might have originated from this deep, unknown part of the Earth. Upon further investigation, researchers discovered that the source of the anomaly could be linked to a significant change in the Earth's internal structure. In particular, the change seemed to be the result of a mineral called bridgmanite, a dense silicate mineral found deep within the mantle. Under the extreme pressure and temperature conditions of the Earth's lower mantle, bridgmanite undergoes a phase transition. It changes from its standard perovskite structure to a new phase called post-perovskite. This transition involves a dramatic change in the mineral's density. As bridgmanite transforms from one crystalline structure to another, it becomes much denser, which in turn affects the gravitational pull in the surrounding area. This sudden shift in density could explain the significant gravity anomaly detected by the gray satellites. Essentially, a portion of the Earth's deep interior underwent a rapid and dramatic change, altering its mass distribution and creating a detectable shift in gravity at the surface. The process is somewhat akin to water freezing into ice, where the material changes its structure and density under specific conditions. In this case, the temperature and pressure deep within the Earth caused the mineral bridgmanite to undergo a similar transformation, with a corresponding increase in density. This change in the mineral structure was so intense that it impacted the Earth's gravitational field, causing the anomaly observed in 2007. This discovery is truly groundbreaking because it suggests that the Earth's interior can undergo rapid structural changes that were previously thought to happen over much longer periods of time. The notion that minerals in the Earth's deep mantle can undergo such swift transformations is a revelation, showing that even deep within our planet, the processes that shape its structure can be more dynamic than we ever imagined. The story doesn't end with the transformation of bridge. There's a fascinating connection between this deep, rapid change and another geological mystery. The African Large Low Shear Velocity Province, LLSVP. This is a massive region deep within the Earth's mantle that has puzzled scientists for years. The LLSVP is an area with unusual properties, notably a lower than expected shear wave velocity, indicating that it is composed of materials that behave differently from the surrounding mantle. The African LLSVP is located beneath the continent of Africa, and its origin and role in the Earth's internal processes are still not entirely understood. What makes this even more intriguing is that the gravitational anomaly detected in 2007 seemed to coincide with changes in this very same region. As the mineral phase transition in the Earth's mantle occurred, it likely interacted with the African LLSVP, causing it to shift or change position slightly. The timing of this event is important because it occurred alongside another significant anomaly, the geomagnetic jerk. A geomagnetic jerk refers to a sudden rapid shift in the Earth's magnetic field. This phenomenon happens when there is an abrupt change in the variation of the magnetic field, and it was observed around the same time as the gravity anomaly in 2007. The geomagnetic jerk is typically caused by shifts in the motion of the Earth's liquid outer core, which generates the planet's magnetic field. The fact that the gravity anomaly and the geomagnetic jerk happen simultaneously suggests a connection between the two events. It's possible that the redistribution of mass in the mantle caused by the bridgmanite phase transition could have influenced the movement of the liquid outer core, thereby affecting the magnetic field. This provides a tantalizing hint that changes in the Earth's deep interior might have a direct impact on the behavior of the planets. Magnetic field, a connection that has not been fully understood until now. Scientists are still working to unravel how these deep processes are interconnected. But the data from the GRACE satellites, along with other geological and magnetic studies, offer a compelling new avenue of research. The idea that shifts in the mantle and the core could influence the magnetic field and gravity at the Earth's surface is a groundbreaking insight that opens up new questions about how our planet functions beneath the surface. These groundbreaking discoveries offer a deeper understanding of the Earth's internal dynamics, challenging many of the long-held assumptions about how our planet works. For decades, scientists believed that the Earth's interior was primarily a slow-moving, stable environment. Processes like tectonic shifts, mantle convection, and mineral phase transitions were thought to occur gradually over millions of years. However, the 2007 gravity anomaly reveals that, at least in some cases, the Earth's interior can experience rapid, large-scale changes within just a few months or years. This new perspective is revolutionary because it suggests that the Earth's internal processes may be far more dynamic than previously understood. The discovery that a mineral transition could cause such a significant change in gravity emphasizes how sensitive the Earth's interior is to even small shifts. These rapid shifts in density and mass distribution can lead to measurable changes in the gravitational field, affecting everything from plate tectonics to the behavior of the magnetic field. In addition to these structural shifts, gravity anomalies provide a window into the planet's evolving composition. By studying these anomalies, scientists can gain a better understanding of the materials that make up the Earth's core, mantle, and crust. This information is crucial for understanding the long-term behavior of the planet, from its geological evolution to its ability to sustain life. Furthermore, the connection between gravity anomalies and the geomagnetic field suggests that what happens deep within the Earth's mantle may have far-reaching effects on the planet's magnetic field. This is a major breakthrough, as the magnetic field plays a critical role in protecting the Earth from harmful solar radiation. Understanding how deep Earth processes influence the magnetic field could help us predict changes in the field and better prepare for the potential effects on communication systems, navigation, and satellite operations. These findings also highlight the importance of continued research using gravity data. The GRACE satellites have given scientists a level of precision that was previously impossible, allowing them to detect changes as small as a millimeter. This precision is invaluable for studying not just gravity, but also water distribution, climate change, and geological shifts. The data from these satellites will continue to be a powerful tool for scientists in understanding the Earth's ever-changing internal processes and their effects on the surface. Looking beyond Earth, these methods of studying gravity anomalies can be applied to other planets and moons in the solar system. For example, similar gravitational mapping techniques are being used to study the Moon, where gravity anomalies have helped scientists understand the structure of its interior. By comparing gravity data from Earth and the Moon, scientists can gain insights into the differences between the two bodies and better understand the processes that shaped both planets. In conclusion, the discovery of the 2007 gravity anomaly and its connection to deep Earth processes is more than just an academic curiosity. It provides a unique opportunity to explore the inner workings of our planet in ways that were previously unimaginable. As we continue to study gravity anomalies and other deep Earth phenomena, we may uncover even more surprising revelations about the forces that shape the world we live on. These insights are not only important for planetary science, but also for understanding the broader universe. As we push the boundaries of our knowledge, we may find that the Earth is not as unique as we once thought, and that the processes we observe on our planet may be part of a much larger, more dynamic cosmic system.